Hey everyone, welcome to The Explainer. Today we're putting on our chemical detective hats for a really fascinating look into the invisible world of acids and bases. We're going to uncover the hidden identities of the liquids all around us, from the juice sitting in your fridge right now to complex solutions in a high-tech lab. Here's our game plan for today's Explainer. We'll start by meeting acids and bases, check out the proton exchange, look at indicators as chemical evidence, dive into water as the ultimate shapeshifter, and wrap up with a quick recap and transfer. We've got a couple of pause checks along the way, so stay sharp. All right, Section 1, meet acids and bases. So back in the 18th century, chemists figured out that acids had a sour taste, which, let's be honest, is an absolutely terrifying way to do science. Imagine just tasting random unknown chemicals to see what happens. No way. In a modern physical science lab, we strictly never taste or touch unknown chemicals. Safety is absolutely our #1 priority. So instead of using our tongues, we rely 100% on safe chemical evidence to tell us exactly what we're working with.
Moving right along to Section 2, the proton exchange.
Back in 1923, scientists Johannes Bronsted and Thomas Lowry came up with this brilliant, modernized way to define an acid. They called a Bronsted-Lowry acid a proton donor. Now, when we say proton in this specific context, we're actually talking about a hydrogen ion. To make this easy to visualize, think of the acid as the pitcher in a baseball game. It's on the mound, holding the ball, and it throws that subatomic pitch, intentionally donating that proton to another substance. On the flip side of that pitch, we have the Bronsted-Lowry base, which they defined as a proton acceptor. If the acid is our pitcher, the base is the catcher, glove-ready, receiving that exact same subatomic pitch. This incredibly fast, completely invisible exchange of a single proton is literally the fundamental relationship that defines acids and bases. One throws, the other catches. Okay, time for a quick pause check to make sure we've got this down. If a substance donates a proton to water, is it an acid or a base? Take a second, think carefully about our pitchers and catchers, and lock in your answer. Got it? Well, it's an acid, and the reasoning is pretty straightforward. Bronsted-Lowry acids act as proton donors. Because this mystery substance actively threw the pitch to the water, it's undeniably our acid. Let's jump into Section 3, indicators as chemical evidence. Since we know for sure we aren't tasting anything, how do we safely gather evidence of an invisible proton exchange? Check out this observation from Robert Boyle way back in 1680. He noticed that acid solutions could actually change the colors of certain natural dyes. This was a massive game changer for chemistry. It finally gave scientists a safe, highly visual tool to identify dangerous chemicals without ever putting themselves at risk. Today, we call those natural dyes indicators. They act as our chemical detectives. By just dropping a tiny bit of indicator into an unknown liquid, a vibrant color change instantly reveals that an invisible proton exchange just happened at the atomic level. It safely proves whether a substance is an acid or a base, all without us having to handle it unsafely. All right, time for our second pause check. If a natural dye changes color when an unknown liquid is added, what exactly does this tell us? Think about the role that color-changing dye is playing in our lab. The answer is that it serves as safe chemical evidence. It confidently tells us we're likely dealing with an acid or a base. The core reasoning here is that indicators respond to those invisible proton exchanges with a highly visible, undeniable color shift. We don't have to see the atoms. We just let the colors do the talking. Which brings us to Section 4, water, the ultimate shapeshifter. Water is incredibly unique because it is amphiprotic. Yeah, that's a pretty big word, but let's break it down. Amphi means both, kind of like how an amphibian lives on both land and water, and protic refers to protons. Put it all together, and it means water has the superpower to act as both a proton donor and a proton acceptor, depending entirely on its chemical surroundings. So water is literally the ultimate shapeshifter. Check this out. When water reacts with ammonia, it acts as an acid, generously donating a proton. But when it reacts with hydrogen fluoride, it totally flips the script and behaves as a base, actively accepting a proton. It plays both pitcher and catcher perfectly, depending on who else is standing on the field. Finally, Section 5, explainer recap and transfer. Let's wrap up this explainer. First, safety is paramount. We always use chemical evidence like indicators, absolutely no tasting. Second, Bronsted-Lowry acids are our proton pitchers. Third, bases are the catchers. And fourth, Water is amphiprotic, meaning it's a versatile shapeshifter that can play both positions. So, I want to leave you with a quick thought to really test your detective skills. Imagine you're in the lab and you find a brand new, unknown liquid. If this liquid accepts a proton from water, how would you classify it? And what safe laboratory tool would you use to prove it? Think about those proton catchers and our color-changing chemical detectives. Thanks for joining me on this explainer, and keep exploring.